Hi, everyone. So today we're going to be talking about hypothesis testing. So hypothesis testing is something that you're going to be doing a lot if you're doing psychology research. So this is really useful if we don't really know what's going on, but we want to get a sense of, is there a reason to think that, say, this intervention works, or this issue is a problem, or do we think that it's an intervention that doesn't work, or is this an issue that's really not a problem? And so this is something that is very useful. So we'll be talking in this section largely about null hypothesis significance testing, which is where you're trying to make a decision in terms of, do we think we should assume for now that there's some difference, or should we assume that there's no difference? So I'm going to walk through how that works in a more theoretical sense, and then we're going to get back to a practical example. And my practical example actually has to do with Raja. So uh, one thing that's kind of silly about Raja is that he's used to being home alone a lot of the time, and now we're around all the time, which he loves. But he's kind of weird because he always waits until he's alone in the apartment until he eats his food. So he has been waiting to eat his food for a little bit too long, and we're trying to figure out, if we leave the apartment for a little bit and go for a little walk, is he going to eat? So we are going to be testing the hypothesis that if we leave him alone for a little bit, he's more likely to eat than if we don't leave him alone. I'll walk through some practical examples in terms of how that works in psychology, and then we'll talk about how we would design that study to see if leaving Raja alone in the apartment would work to make him want to eat his food. So we'll jump into some examples. I have a little PowerPoint presentation to go over. Right, so if you want to test a hypothesis, the first thing that you're going to want to do is specify a research hypothesis. So a research hypothesis is a claim that you as a researcher make about what you expect will happen in a given situation, or how you think that variables are related to each other. And so it is a claim about how you believe that people think, or that they feel, or that they'll behave in a given situation. So for example, you might have a hypothesis that if you listen to music, you're less able to pay attention to things. So more specifically, listening to music reduces your ability to pay attention to things. Or you might think that two variables are related to each other. That is, there's a correlation such that intelligence is related to personality in some way. At this point, we don't have to be super specific, but you should be saying what the variables are and give a sense of how they're related to each other. So here are a few examples of hypotheses that aren't that great. So you might have these general ideas, but it might be impossible to test those ideas. It might be so vague that you really don't know how to interpret it. So if you're saying love is a battlefield, that's the example in the textbook. I don't really know how you would test that, how you would examine it, so that's not a very good hypothesis. You also might have a claim that by definition is true. So if you say that introverts are introverted, you could look, and if someone scores 6 on an introverted scale, they're high in introversion. So that hypothesis would end up being true, but it's always true. So there's no real point to testing that. And you also shouldn't just be making a claim about how the results will turn out. If you're making a psychological hypothesis, you should be saying things about a group of people or people in general. It's not just about what you expect your specific participants to do. Because again, we're using these samples to try to make inferences about a population. So after you have your research hypothesis, you want to be more specific and state a statistical hypothesis. So this is when you have a mathematical argument about how you would expect the data to turn out if you run the study in a specific way. So for example, in a study I did recently, I was looking at what encourages people to support transgender rights. And the hypothesis I had there is that people who have a transgender friend will have more support for transgender rights than people who do not have a transgender friend. So I was able to give a survey, and I compared participants who had a transgender friend to those who did not have a transgender friend. In the example I was talking about, I had a hypothesis about how much Raja will eat food. And so you can also have a hypothesis that there isn't going to be any difference. So in this case, it might be that Raja will eat the same amount of food whether or not I am in the apartment. This breaks down into two different types of hypotheses, a null hypothesis and an alternative hypothesis. So for any hypothesis testing that you do, you're going to want to specify both a null hypothesis and an alternative hypothesis. So if we looked at our examples here, we could think about whether these seem to be a null hypothesis, that there's no difference, or an alternative hypothesis, that there will be a difference. So let's look at that first example there of people who have a transgender friend will have more support for transgender rights than people who don't have a transgender friend. So that is an example of an alternative hypothesis, because we're arguing that there will be some sort of difference, that levels of one variable, support for transgender rights, is related to another variable, in this case, whether or not someone has a transgender friend. So let's imagine we wanted to turn that into a null hypothesis to compare those. In that case, we might say that people who have a transgender friend have the same amount of support for transgender rights as people who do not have a transgender friend. So then we'd basically be saying, it doesn't really matter whether or not you have a transgender friend for how much you support transgender rights. So then let's look at the second example here. For whether Raja will eat the same amount of food, this is saying that it's the same amount whether or not I'm in the apartment. So this is an example of a null hypothesis. Let's imagine we wanted to turn that into an alternative hypothesis. We might want to say that Raja will eat more food when I am not in the apartment as compared to when I am in the apartment. So that's one example of an alternative hypothesis. Again, how you frame this will depend on what you expect. I could also be making the opposite argument that maybe I need to be in the apartment for Raja to eat his food for whatever reason. And then my alternative hypothesis will be Raja will eat more food when I'm in the apartment than when I am not in the apartment. This, again, is following up on your research hypothesis. So based on running studies or based on your own experiences or whatever it might be, you have these ideas and then you're specifying this is what we would expect the outcome to be at the end of the study. So you can be interested in either the null hypothesis or the alternative hypothesis, but in psychology, a lot of studies are focused on that alternative hypothesis. So we're usually interested in things like whether people with different personality traits behave different at work. Does an intervention improve symptoms in a clinical setting, or does it have no effect on clinical symptoms? So often the thing we're most interested in is the alternative hypothesis true? Is there a reason to think that there will be a difference based on what intervention we do, based on the personality traits, and things of that sort? And so you often find that the alternative hypothesis is the primary hypothesis we're making based on our research hypothesis. And if we don't find support, then we hold on to that null hypothesis that there isn't actually a difference. When you're testing a hypothesis, you're then concluding either there seems to be support for our hypothesis, there is a difference, or there is not. So unfortunately, there is some chance involved in that. So maybe there is no real difference, and just by chance, it looks like there is a difference. We could be wrong in that way. Or maybe there really is a difference out there in the population, but our sample just didn't show that difference, again, maybe because we got unlucky. So basically, when you're making these decisions of do you retain the null hypothesis, that is, Do you assume that there's no difference? Or do you reject the null hypothesis, assume that there is a difference? So maybe it's the case, like in the top left, that there is no difference in the actual population that you're trying to study. And you conclude that there is no difference. You made the correct decision. You can also conclude that there is a difference. So maybe in my example, you find, like I did, that those who have a transgender friend have more support for transgender rights than those who do not have a transgender friend. And in the actual population you're studying, that's true. Again, you made the correct decision. So you might make an error with that. And so you might find that in the population, there's actually no difference, something doesn't matter, but you happen to find just by chance some positive looking results. That would be an example of a type 1 error. If you have the opposite, like down here, where you conclude that there's no effect, but really out there in the population, there is an effect, that is a type 2 error. So of course, ideally, we are going to find results that generalize to the real world that hold up. We don't want to make any type 1 errors or any type 2 errors, but unfortunately, there is always a chance that we're going to be making one of those errors. So we want to try to account for, what is our chance of making these errors, and how do we reduce that? So in terms of type 1 errors, that is something that we are able to specify specifically as part of our research design. So we decide how improbable, based on the null hypothesis, the results would have to be for us to say, okay, we think there is really a difference going on here. And so we use a cutoff point referred to as a significance level. And the symbol for that statistically is the alpha level. And so this is the type 1 error rate for our study. So by default, we usually set this at 5%. So we're comfortable with there being a 5% probability that we would get results that seem to support the alternative hypothesis just by chance, assuming that there was nothing going on. And so probabilistically, this is 0.05. You also will have the power of a study. So power is a good thing. The more power you have, that's basically here making the correct decision to believe that there's something going on when there really is. And so the type 2 error rate is 1 minus the power. So let's say that we have 80% power in a study. Then there would be a 20% type 2 error rate, which would basically mean if we run the study that specific way, 80% of the time, we would find that the hypothesis is supported if there really is an effect in the population, and 20% of the time, we would not. So you might be wondering, why is it 5% for type 1 and 20% for type 2 just by default? So this is something that has become a convention. And part of the thinking behind this is we're more concerned with finding results that seem to suggest that something exists that doesn't, than running a study and not finding support for something that actually does exist or that there actually is a difference. So it's essentially by default being more concerned about a type 1 error than a type 2 error. So that might not be the case for all studies, and there's a lot of debates among statisticians about which one of these error rates you should be more concerned with. But this is something we can get a sense of for a specific study. Again, ideally, we're limiting type 1 error rates and type 2 error rates at the same time. So part of what makes this a little bit difficult is that there's a bit of a trade-off between type 1 and type 2 errors. So let's say that we decide to make it so that you have to have really strong evidence to support the alternative hypothesis, reject that null hypothesis. That is, concluding that, say, an intervention is effective in the population. So if you have that really stringent criteria, you're limiting type 1 errors really well. You're saying, okay, it's going to be very unlikely that we would just get this chance finding that supports the idea that this intervention works. What ends up happening is that when you're decreasing that type 1 error, being more stringent, that can actually increase type 2 errors. So the harder it is to reach that level of significance, the less power you have in your study. And so that is always something that you need to think about, in that if you say, okay, I'm going to need really, really strong evidence, then you're going to be missing out on discovering things as much as if you do the opposite. And let's say you say to yourself, well, I really want to make sure that I find support for a hypothesis. If there is really something going on in the population, you can do that by being a little bit more lax with that alpha level, like say make it 20%, and then you're going to have more power. But then the drawback to that is you might be finding a lot of things that seem to be different or seem to support your hypothesis that are really just statistical errors, are just chance findings. So this is something, we have to consider both of these at the same time. So when you're deciding on how you're going to be using hypothesis testing, you're going to be using a test statistic. And so this is a statistic that you're using to make these decisions. So do the data seem to be consistent with the null hypothesis, or do the data seem to be consistent with something else, something that is not likely to be observed by random chance based on the null hypothesis, in which case maybe the alternative hypothesis seems like it could be true. So there's always going to be, a distribution of that test statistic. There is what's referred to as the sampling distribution of the test statistic, which is if you imagine that the null hypothesis is true, that there's no difference, just by random chance, it's usually going to be right near the middle, and sometimes it's going to be higher, sometimes it's going to be lower, like we were talking about with binomial and normal distributions. And so, for example, if you're making random guesses and you get, 100 random guesses where it's basically a coin flip, you would expect that you'd get 50 right on average. And then there's also going to be a sampling distribution where if you're randomly guessing, sometimes it's going to be over here by 60, sometimes it's going to be over here by 40. Every once in a great while, it might be even way out here. It's so improbable that you can't even see those bars anymore, or way over here. And so you have what you would expect by random chance if there was really nothing going on at all except for just luck. And then based on that sampling distribution, you have a critical region, which is the values that are extreme enough that you would reject the null hypothesis. And you would conclude that your hypothesis was supported by the data. So with this, you have critical values, and that's when you have any values outside the range that you would expect by random chance. So again, with that binomial distribution, where you have 100 guesses, and it's a 50-50 chance each time, if you are using an alpha of 0.05, that means if it's in the 5% least probable outcomes, if it's between 40 and 60, that would suggest that your observed outcomes aren't extreme enough for you to believe that there is really a difference. But if it's less than 40 or greater than 60, then that supports the alternative hypothesis that there is a difference, that your results are more extreme than you would expect just by chance. And we'll be going through a few different examples of test statistics, but the same logic applies, where we're looking to see if it is within the critical region or is not within the critical region. So there's a phrase you might have heard many times before, statistically significant. And basically what that means is that if you reach the critical value here, less than 40 or greater than 60, we conclude that the results are statistically significant. So statistically significant is sometimes misunderstood because significant sometimes means big or important, but really what it means when we're using it in hypothesis testing is that if the null hypothesis were true, we would expect that result or more extreme to not happen very often. And so we think maybe there's something other than the null hypothesis going on. And that's really all it means. And so when we're doing this hypothesis testing, we have these critical regions. This is a case where there's an alpha of 0.05, and we're doing a two-sided test. So that's the most common, where you basically split it up and you say 2.5% of the distribution over here, 2.5 over here. You can also do what's referred to as a one-sided test. So with a one-sided test, let's say the alpha was 0.05 again, you would say maybe ignore the lower end, and you'd be looking specifically at the upper end, and you'd only be including the upper 5%. And maybe the blue region would be moved over here a little bit, and you'd say if it's at least this extreme, then that supports the alternative hypothesis. But if it's anything over here, including the bottom, then that's consistent with the null hypothesis. So often in psychology, we use two-sided tests. Again, that's kind of a convention that we aren't necessarily sure how the results will go. It might be hypothetically possible that it'd be extreme on the top end, or it could be extreme on the bottom end. Maybe we have some very strong reason to believe that it would only make sense if the results went one way, and it wouldn't really make sense if it went the other way, in which case we might want to specify a one-sided test. So one-sided test, all things considered, has a little bit more power because it's easier to reach this point, but then we aren't able to see if it is more extreme in the opposite direction. So this is something that you would also want to consider as well before you run the study. So when you get this value, so let's say it was over here, and you might get a p-value at this point somewhere around 0.02. So that is that there's a 2% probability that you would get that extreme of a score or more extreme. And so this p-value is something that we're often looking for when we're doing hypothesis testing. So if the alpha level is 0.05, we're looking to see is the p-value less than 0.05. And if the p-value is less than 0.05, that is when we conclude that the difference is statistically significant.